So we understood what is convolution and we saw the properties of convolution, and we also learnt that for any LTI system, the output is given by the convolution of the input signal with its impulse response. Once again, keep in mind this is true only for LTI system. Now, using the properties of convolution, we can learn more about the properties of an LTI system itself. So remember, when we talked about systems, we saw some properties of systems. We talked about its memory, its causality, its invertibility, and its stability, and so on, right? Now, if we say that a system is linear and time invariant, we have already characterized the output just in terms of only one signal, which is the impulse response. So if you know the impulse response, you know everything about the system. That's what we said, because you can tell what would be the output for any input just by convolving with impulse response. Now, can we also tell what are the properties of the system? Can we comment about its memory, causality, invertibility, stability, etc. just by knowing the impulse response? Our earlier notion was that we will know the impulse response because it tells us everything about the system, which means it should also tell us about its memory, causality, invertibility, and stability. Now we'll see if it actually tells us that. Okay, and we'll understand all these things through the properties of convolution itself. First question is, does an LTI system have memory if an impulse response is given to you? So what does memory mean? Memory means that you have the output to be dependent upon not just the present input but also on the past. So which means when you are convolving the impulse response with the input, the impulse response should take into account not just only the present input but also the past input. So what is impulse response? So let us say your input is the rectangular function 0 minus half plus half, and let us say our impulse response, let's say this is x of t, your impulse response h of t is now looking like this. Let us say, for example, 0 and 1. Okay. Now what happens at y of 0? How would you compute y of 0? You would basically time reverse h of minus tau, okay, and then put it at h of t minus tau, which is basically t is equal to 0, which is this point, and then find out the product of these two signals and then find their area. So the product of these two signals now is going to include, this is minus 1, right? So we have here the output at 0 is depending not only on the input at 0 but also it is depending on the previous inputs at minus 0.1, minus 0.2 up until minus 0.5. So clearly the system has memory. So when can you say an LTI system does not have memory? Only if the output at every point depends on the input at that point alone. That can happen only if the impulse response is a Dirac delta function, a scaled Dirac delta function. So it is easy to tell what would the memory of an LTI system be just by looking at the impulse response. If the impulse response is a scaled Dirac delta function, then you say that this LTI system does not have any memory. It is just going to give whatever is the input by scaling it with some factor. It is like an amplifier. It is just like an amplifier. It is just going to either increase or decrease the amplitude level and then give the input as such. It is not going to do any other kind of operation processing on top of it. So this is a memoryless LTI system. So if the LTI system has an impulse response which is not equal to the Dirac delta signal, then definitely it has memory. You can easily say that. So it is very nice that we can comment about these properties just by looking at the impulse response. What about the next property? So the next property is causality. So what does causality means? That the output at a particular time instant depends not only on the input at that time instant but also input from the future. That is a non-causal system. So if it is a causal system, the output at a particular point should depend only on the inputs that are there at the present and at the past. So let's take this same example. So in this particular example, as you can see here, the output at any point is going to depend only on the input which was at present and the past. So, the output at time t equal to 0, which is y of 0, is the area of the product of these two signals, okay, which is basically right this area. Now, what if you want to compute the output at, let us say, y of 1. So, when you want to compute the output at y of 1, you would have the signal to be multiplied with the time reversed version shifted by 1, which is nothing but this is 0 and this is 1. So, this was the actual impulse response, you time reverse it, you get this impulse response and you shift it by 1. Now, you compute the area here of these two products. That will be the value at y of 1. So, if you can see here what happens at each and every point, when you try and compute the output at 0, you are taking into account the input that was present at 0 and before 0. When you compute the output at 1, you are taking into account the input that was present at 1 and that was present before 1. So, the input in the future, that is after greater than 1 or greater than 0, is never taken into account in computation of the output, which means this system is a causal system. That's great. Now, causal systems are practical, you can implement them in practice, so it's really good for us. Now, what is a non-causal system? How would its impulse response look like? So, if the impulse response makes the system to give an output which is dependent upon the future values, then it is non-causal. A very simple example would be, now just simply take this impulse response. This is h of t. Okay. Now, what if this was the impulse response? Let's see what happens if this was the impulse response. Now, what is the time reversed version? The time reversed version would look like this. This is h of minus tau. If I want to compute the output at y of 0, then you multiply your input signal x of t with h of minus t. Find the product and compute the area. So, as you can see here, in order to compute y of 0, you would be multiplying the signal from 0 to 1, which means the value of y of 0 depends upon the value of the signal at 0, 0.1, 0.2 up until 1, which means it is dependent upon the future values. So, whenever the impulse response has non-zero values on the negative values of time. So, here h of t is non-zero only for negative values of time. So, for this kind of impulse responses, the system is non-causal. So, let us take a very standard signal that we have been using, this signal, right. So, if this was the signal that was the impulse response, then what happens here? The output at time t equal to 0 is the area of product of these two signals. Now, as you can see here, so here the impulse response has non-zero values for both negative time and positive time. So, when you flip it, whatever was the impulse response corresponding to the negative time comes on the right hand side, and that gets multiplied with the portion of the signal which is present in the future, right. So, this portion is the future, because you are trying to compute y of 0. So, if you are computing y of 1, or let us say y of, let us say 0.5, then you would shift the signal by this much. So once again, as you can see here, the portion of the impulse response which corresponds to the negative time, here this region corresponds to the negative time, right? So that region, so whatever corresponds to the negative time always starts appearing at the future values of the input. So here we were trying to compute y of 0, and this negative time part is now getting multiplied with y of 0.1, 0.2 up until 1, and in this case we were trying to compute the output at 0.5, and the negative part was getting multiplied with 0.6, 0.7 up until 1. So whenever there is a non-zero negative time part for the impulse response, they contribute to the non-causality of the LTI system. So you can say that the LTI system is non-causal if it has non-zero values of the impulse response for t less than 0. So if the impulse response has only 0 values for negative values of time, then you can say that the LTI system is causal.